Hello and welcome to E233. I'm your instructor, Gregory Myers. This video, we're going to take another look at an older version of our P5. This one's focusing on our physics demo and the series associated with that. And specifically what we're going to do is we're going to take a look at our projectile 1D version 4 function and some of the behavior associated with it and how we're going to separate out the responsibility of calculating the values with presenting the values. This video assumes that you've watched the earlier videos focusing on how to set up the command line switches and some of the videos associated with parallel arrays. So let's go ahead and get started. You'll note here that we are passing a y init by val, and we are then passing multiple parallel arrays, our time, y time, and vy time, that are ultimately going to be controlled by n. And n is just simply the number of elements in the array, or rather the number of elements that the user would like to see calculated. The total number of elements in the array, since we will still be dealing with statically declared variables, will be handled by a constant n max, and we'll get to that in just a little bit. But to begin with, what we're going to do is we're going to navigate first to the function, and we're going to take a few minutes to go ahead and update the comments associated with this function. I'll spend a little bit more time on this one, and then I'm going to allow you for some time to focus on the other ones. But to begin with, what we want to do is we want to document then the name of the function. And I like to keep this simple. I simply use the entire function signature here. And then the description of the function, which allows for us to calculate 1D motion using parallel arrays. And then for the argument list, then we simply go through each one of the arguments, providing a brief description of what each does. We'll start off with the double for y init, and that is nothing more than the initial height. As I mentioned, it is passed by val. We have the double of our time, which is actually an array of times from t init equal to 0 to whatever our TFinal happens to be. We have another array, our v or y time rather, which is also an array of doubles, but it's an array of heights from y init to y final, which is equal to 0. And just to keep consistent here, we'll do the same thing for our t init. And then our vy time, which is an array of velocities from v init, or rather vy init, equal to 0 to whatever the vy final is right when it hits the ground. We also have our int n, which basically keeps track of the number of elements used. It's not the total number of elements in the array, but it's the number of elements used in each one of our arrays. And then lastly, we have the int return value that will either be success or failure, depending on, in this case, if any of our command line, or excuse me, any of our arguments to our function fail validation. And so to begin with, what we want to do is we want to look at each one of the arguments and apply some basic rules to them. For instance, our y init should not be less than 0. For this example, our n, for instance, we have a stipulation that we'd like to have at least 2 values. And we can also check to see if our time, y time, and vy time vectors or arrays are null. And so to begin with, what we'll do is we'll start validating our arguments, starting with our y init. And if for some reason our y init is less than 0, or for that matter, what we can do is we can actually specify if it's less than or equal to 0. Then we simply print a message, printf, error, please provide a valid or a positive initial height. And then we also want to simply say results are equal to exit failure. And at this point, if you'll note that we return the results, then basically it means that our function did not work correctly or didn't validate correctly. Continuing with this, then we have our else if. We can just simply go through each one of our arguments. I'm going to go ahead and lump together the time, y time, and vy time. So what we'll do is we'll check to see if our time is equal to null, or our y time is equal to null, or our vy time is equal to null. Any of those three scenarios are met, then we simply say printf error, please provide valid arrays. Now, it's not likely we're going to encounter in this scenario in this particular project, but it's a good habit to get into to check to see what all of your input arguments are. Ultimately here, we have results are equal to exit failure. Continuing on, we said that we want to make sure that our n is at least 2. Now, technically, we could have n equals to 1, but what I'd like for us to be able to do is to actually print out both a t initial and a t final, as well as a initial and final height and velocities. And so ultimately here for this scenario, then we need to have an n equal to or greater than 2. So what we want to do is we want to check if n is less than 2. And if n is less than 2, once again, printf error, please provide an n larger than 2 or greater than or equal to 2. And once again, results equal to exit failure. And then the other scenario that we want to check is to make sure that somehow the user did not provide an n that was in fact greater than n max. And in this case, what you can do is you can actually leverage the n max constant and say error, please provide an n less than %d. And for that %d, what we're going to do is we're going to populate it with whatever the value of the n max constant is. Now, I have not yet declared that n max constant. And what we'd like to do is come up here to the top, go ahead and define a couple of things actually. Number one, we can go and define our n max, and we will simply give it a rather arbitrary value of 100. And then we can also go ahead and define, which we know we're going to need, our AY, and that'll simply be negative 32.2. And while we're thinking about it, even though we're not covering it in this video, we're probably going to need an AX, which we are going to define as 0. Continuing on with the things that we need to handle up here at the top of the file, we probably need to go ahead and recognize that we may be using our string library, so string.h, but we know for a fact that we will be using our math.h. So go ahead and add those to your list of includes. And then let's go back down to the function itself. And if we've validated all of the input arguments to our satisfaction, and we also need to go ahead and put results equal to exit failure. on the last scenario, then what we're left with is nothing more than to simply do the calculations. And so at this point, then, if we've managed to validate our input arguments by essentially not tripping any of the else ifs, and we've landed in the else, then we need to do something. Well, what does that look like? Well, the first thing that we want to do is we want to calculate our TFinal, and then we want to break up the TFinal minus TInitial into segments of time known as TDelta based on n. N is the number of data points that the user wished to calculate the time, height, and velocity of our projectile. And so we'll go ahead and get started by providing some additional variables, least of which is going to be a double for our TFinal. We should probably go ahead and provide another double for our TInit. We can do the same thing, not for our YInit, because we're provided that through our function signature, but we can also go ahead and provide a variable for our YFinal, as well as the VYInit and VYFinal. Now I'm going to come back to the YFinal in just a second. We're actually going to see that we're going to leverage our Y time array, but we will need the VYInit. And we're also going to need a TDelta. And the TDelta is simply going to be what breaks up our total time from TInit to TFinal into segments. And then lastly, we're going to need an administrative variable, if you would, that we're going to simply call index. And that's going to allow for us to cycle through the times from TInit to TFinal. So let's go ahead and initialize some of these. Our TInit will be equal to 0. This just allows for some future expansion on our part. We can go ahead and initialize our TFinal, but we're also going to be calculating it very shortly. And likewise, our TDelta equal to 0. Same with our VYInit, which we will use later. And then we can initialize our index, but we're immediately going to use it in a for loop, which is going to initialize it anyway. So first thing, as I mentioned, we're going to go ahead and calculate our TFinal. Our TFinal is just going to simply be the square root of -2 times whatever our YInit is divided by our AY. And what we want to do now is we want to handle the shift associated with our TInit. And in this particular case, then our TInit, we simply add on to the end. Now, in this case, it's 0, so it's not going to impact us any. But then what we can do is we can calculate our TDelta based on the time difference between our TFinal and our TInitial divided by n minus 1. And now the -1 part might not seem intuitive, but effectively, if you have n data points, you're going to have n minus 1 segments. And so a common example that I give people is there are 13 tick marks on a 12-inch ruler. We tend to forget the 0th tick mark, but basically, if you want 13 data points, you have 12 intervals. In this particular case, if you want n data points, you have n minus 1 intervals. At this point, we can go ahead and build our for loop. So for index equals to 0, index less than whatever the value is for n, index plus plus. And then what we'll do, we'll start off with our time vector. And so our time vector, square brackets index, is just simply going to be equal to whatever the initial time is, plus then what the index times our TDelta. Now, continuing this, we can do the same thing now for our Y time. Y square brackets index is going to be equal to Y init plus our Vy init, which also happens to be 0, times our time square brackets index plus then 0.5 times at squared, 1/2 at squared, or a underscore y, times then the pow function of our time vector at the current index and the exponent 2. Lastly, we can do the same thing now for our Vy time square brackets index is just simply equal to our Vy init plus a y for the acceleration times the time and then whatever the index is at the current iteration. At this point, we should be done with our function. Now, before we leave this function, I want to take a second to point out that you'll notice that we're not printing anything other than the error messages. The responsibility of printing the table and printing to the file both are left to the main. This is the reason why we want to pass these arrays essentially by reference so that they may be updated inside the function and then they can be used elsewhere in our program. And so before we leave this function, let's go ahead and build it just to make sure that we haven't introduced any bugs. And then let's get started on our main. Now, in an earlier video, we've already handled the triaging of the switches, the /1d, /i, /1d, and /p, and so on. And you'll also notice that as we go through this, we're going to have a little bit of redundant code in these branches because of the fact that both the branches are going to be responsible for printing the table as well as printing to the file. And so what we want to do is we want to go ahead and grab a copy of the sample as well as the instructions, and we'll start first with the data that we're wanting to print to the console. In this case, you've got this nice little table here that we can borrow some of the formatting from. And so what we want to do is we want to make a call to our function. And so to do that, we'll just leverage our results variable. And we'll say results are equal to projectile 1D version 4. And we want to pass to it the y init. But now we also need to have the vectors associated with the time, the y time, and the Vy time. Now you'll notice that we haven't yet created these. We're going to go ahead and use the names that are suggested to us by the function signature, and that is going to be time, y time, and then Vy time. Keep in mind that we do not have to use those names necessarily. And then we also want to pass an n, which is going to keep track of the number of active rows in our vectors. Now, up here at the top, along with our y init, we also want to go ahead and declare a time vector. And what we're going to do is we're now going to use that n max constant to declare a time vector that is far bigger than what we would ever need, unless the user, for instance, asks for a really high number of values to calculate. In this case, we've capped it off at 100, but we can also go larger. We're going to statically define or declare these arrays, and keep in mind that we're not going through and initializing each one of the values. We're going to have that responsibility be handled inside the function and only for the values, or rather the number of values specified by n or specified by the user. So long story short, this is probably going to be too large. However, we're going to go ahead and do the same thing now for our y time and also for our Vy time. Now, at this point, we probably are ready to go ahead and once again build it just to make sure that we've not introduced any additional bugs. And then we can get down to the business of actually printing out our table. Now, first of all, we want to take advantage of our results variable. And unless we are successful in running the function, there's no reason for us to print out those results. So the first thing that we want to do is set up an if statement that leverages the results And if results are equal to exit success, well, we want to print the table. In other words, do stuff. Else, simply provide another message back to the user, printf, error, failed to call or failed to run the function successfully. And remember that we have some additional print statements inside the function. We'll hopefully provide some additional feedback to the user. Now, at this point, we want to focus on the do something part. And first, we're going to look at the table in our P5 sample. And we'll start off with the column header with name and value. And then you can also go over here and simply capture then or repeat what we've got here in the sample. Another printf followed by a new line. And then once again, this just makes a nice looking table. And I would encourage you to go ahead and copy and paste this maybe into Notepad, because we are going to find ourselves using it again. Now, what we can do is just line by line print the name and the values associated, starting with our y init. And for the y init, we could leverage the y init variable, or what we can find ourselves doing is actually leveraging then the y time vector. But either way, we're going to leverage the %8.4f format spec that we've been already using for these projects, followed by a new line. And then what I'd like to do then is just use the y time vector, and specifically for the y init, I'm going to use the 0th element in the y time vector. I can do the same thing now with our y final, also in feet, also using the %8.4f followed by the new line. And now what we can do is we can leverage not the nth value, but the n-1 value. And once again, just to remember, if we were talking about 11 data points, then we would looking at index from 0 to 10, hence the reason to have n-1. The 10th element or the index equals to 10 in as the 11th element in a 11 element array. Now, a little bit of careful copying and pasting. And as long as we have roughly what we have in the sample file, particularly we have our tinit, which is in seconds, and we leverage our time vector, and for our TFinal, we simply leverage our time vector as well as changing the units to seconds. And now we have our time and our y time handled. Let's go ahead and handle our vy init, which corresponds then to feet per second. And more importantly, v_y_time, but the 0th element. And then lastly, our vy final, also in feet per second. Straighten out our table a little bit. Change the variable name. And probably about the only other thing that I would include in this table, which is technically not in the sample, is number of elements. So how about if we just provide elements or number? And in this particular case, what we can do is this will be a %d followed by a new line, and then simply add. All right, so at this point, then let's go ahead and build it once more. And let's test it to see if we've made any progress. So notice here I'm already in my P5 disk debug min-gw Windows folder. Type in dir, there's my p5.exe. We've already tested our switches, so we can jump straight into /1d/i. And for the initial height, we'll put in 100. for the number of data points, 11. And you can see I have a nice little table here. It shows me my T init, my TFinal, my Y init, my Y final, my VY init, as well as my VY final. However, it does not show me all of the data points. In other words, I want to see all 11 calculations. And all we focused on for the purposes of this table are the beginning and the end values. Instead of writing these to the console, what I'd like to do is I'd like to go back to the instructions, and I'd like to see how we should handle this by outputting this to a CSV file, specifically one with n rows and 4 columns, where the first column is the index starting with 0, the time associated with that index, the Y and the VY. And so what we're going to do is we're going to write the output of those arrays, those parallel arrays, not to the console, but rather to a file so that we can persistently use that file. In other words, we can open it up in another application. And so what we'll do here is we'll simply add on or compound what we've already done with this table by opening and writing to a file. Well, to do that, we first need to start off with a file pointer. And so we'll call this one output. And it would probably be beneficial for us to also have some sort of variable that allows for us to go through each of the elements in our array. And that will once again just simply be handled by an index variable. And so the first step that we want to do is we want to open the file. And so we'll say output is equal to fopen. And in this case, we want to go ahead and hard code the file name because it was specified in the instructions. And that is going to be projectile_1d_v4.csv. Once again, each project will be different, but we want to open this one for writing. And we want to check to see whether or not we were successful at opening the file. And if we were successful at opening the file, then we should have a non-null file pointer. In other words, if our output is not equal to null, do something. Else, we have a problem. And we'll handle that scenario first because it's pretty easy. We're just simply going to say printf error, failed to open output file. And you can get fancier. You can describe what file name you were trying to open, etc. But for right now, we just want to provide some sort of message back to the user. Now let's get back to the positive branch on our if statement. In other words, we've opened the file successfully. The very first thing that we want to remember to do is to go ahead and close it. So toward the end of the if branch of our if statement, we want to simply close the file. And then in between there, we want to loop through using our index, starting at 0 all the way up to, but not including n, all of the elements in our parallel arrays. And to do that, we simply say for index equals to 0, index less than n, index plus plus, and we will use fprintf, not printf, but fprintf to print to the output file pointer the format spec associated with a 4-column CSV file, where the first column is going to be the index. The second column will follow the %8.4f format, and each subsequent column after that will also follow that. So you should see now the %d for the index and the 3% 8.4fs will all correspond to the time, y time, and vy time. So it's just a matter now of populating that first with the index. And just so that this doesn't get too long, I'm going to go ahead and jump down to the next line. We have index, we have time, square brackets, index, our y time, square brackets, index, and then lastly, our v_y_time, square brackets, index. And what this will do is this will simply take this first value, put it in the first placeholder, second value, put it in the second placeholder, third, fourth, and so on. The only thing missing then on this format spec is our new line. And at this point, then we should be writing then a nice little table of values to a CSV file. And to see if this works, let's go ahead and build this. We have a error. We had already declared the index, just didn't scroll up far enough. And then we'll go ahead and build it. We'll go back to our command line once more, run our /1d/I, put in the initial height, the number of points. And then at this point, if you type in dir, you should now see projectile 1D version 4. And more importantly, if you go to the folder where your project executable is, you can simply drag and drop this into NetBeans, and you'll see that we did, in fact, successfully write the output. Now, notice the leading spaces here are just simply a result of the %8.4f. In other words, we have a total of 8 spots allocated for that format spec. Once again, that's not a problem in this particular example, but you notice that our first column is the index, the second column is the time, third column is the height, and the fourth column is the velocity. So what do you do for the parametric version or the parametric switch? Well, regrettably, what you have to do is copy and paste. And this is the one downside to this particular approach, is you have a little bit of redundancy. Now, you can handle this by having a separate print function, but we're not going to cover that in this particular video. Instead, what I want you to do is very carefully, starting with your results, all the way down to the close of the curly braces associated with checking to see if your results were successful, you simply copy, and you paste it in to the branch associated with running your function parametrically. At this point, we can go ahead and build it once more. Make sure that you have not opened your .csv file in Excel. But if you rerun this now with a /p/111 again, you'll see that we get our table and our file is still there. And just to prove that we've actually accomplished something, I'm going to change my last value to 21. In other words, I'm going to provide more data points. And sure enough, our file is updated. And so what you get with more data points is just a little more granularity in your results for your time, Y time, and VY time calculations. At this point, then you can simply put some of these switch combinations into a batch file. You can use the piping to allow for you to input arguments automatically, basically everything that we've done in our earlier projects. I'm going to go ahead and stop this video here to allow for you some time to work on your 2D and beam versions of this problem, because effectively it's the same concept. You start by creating the arrays, passing them to the functions. Inside the function, you do the calculations, update the arrays, and then back outside the function, then you're going to be responsible for printing these tables. So as always, hopefully you've found this video useful. If you have any questions, comments, or concerns, don't hesitate to reach out to me. And thank you for watching.